Yeah, I guess. Okay, so now the potential energy. Let's make up numbers. Let's say this is 50. Let's say this is 10. Who could tell me in kilojoules? Right? You gotta have units. What is the value of the delta H for this diagram? Same people keep raising their hands. So I'm gonna go with John Todd. Negative 40 kilojoules. How do you get that? 10 minus 50, right. So here's your delta H. Here's your delta H, and that's negative 40 kilojoules, right?
Do we have to do that on a test?
Yes. I'm going to give you a reaction, and it's going to have something like A plus B yields C, and then I'm going to give you a certain amount of heat or a value. I believe, I can't memorize every question, but you're either going to have the energy over here, 40 kilojoules, or it's going to be on the chart. You're going to have to understand where that section is and how to get that answer. Because you're going to need to know if this is negative because it's releasing heat. Remember how we learned a long time ago on table I that negative means releasing heat, positive means gaining. So you are going to have to be able to explain that.
Why isn't it positive?
Because you're starting at 50 and you're progressing through and ending at 10. So if you start with 50, think of anything. You could think of 50 bananas. You start with 50 today, and by the end of the day you have 10. That means you lost 40 bananas. The concept there is you lost 40 something. What is it? Energy. So you started with 50, you lost 40, now you ended up with 10. That's why it's losing. That's why it's negative, because it lost energy by the time you ended up at a product. Does that make sense? You sure? Yeah.
The reaction thing.
Yeah.
What signs does the negative go on versus going on the spot?
If it's exothermic, it goes on the product side. And if it's endothermic, so if we had the opposite, so if you had something like this, so here's your delta H, that's a positive delta H, it would be A plus B yields C, and then that would be 40 on the left. So if it's endothermic, it goes on the left, exothermic, it goes on the right. That's actually really important for today, because yesterday the video showed you concentration and pressure. We'll learn pressure today. And then if we have time, we'll start talking about temperature and how that affects the balance here, the seesaw, right? So we'll talk about that. All right, so let me go through the other parts quickly here. Who can tell me what is right here at the top? Michaela. Activated complex. What happens there? They start colliding. What the English guy said? Fruitful collisions, only if they have sufficient energy or proper orientation, right. What's this called? Raise your hands, please. That arrow from here to the top of that peak. Zach. Activation energy. That's the energy required to start the reaction. Good. What about from the P up to the top? Abby, remember what that one's called? If this is the activation energy of the forward reaction, this is the activation of reverse. If we go back to A and B, and that's what equilibrium is all about, right? It's what we're learning right now. It's how I can move these weights back and forth. So that's the activation energy of the reverse. What if a catalyst is added? Jess, what happens?
Speeds up the reaction.
Speeds up the reaction. How would I show that? Dotted line underneath it, right. Dotted line underneath it. And Desiree, how does that change the reaction rate? She said it speeds it up, but how can I show that? Or what does it do to the diagram? I'm being a little vague. I'm not asking it very well. How does the catalyst actually speed it up? What does it lower? Go ahead. No?
No, that was my question.
Oh, okay. I think Jess knows.
Lowers the activation.
Lowers the activation energy, right? So it lowers this arrow. If it takes less energy to start, it will start faster. It will start faster. So that's the gist of it. That was a crash course. Questions? Any questions?
So catalyst lowers activation.
Catalyst lowers activation energy. Yep. And remember, a catalyst doesn't take part in the reaction. I use the analogy of a teacher or coach. They can't take the test. They can't play in the game. They just help, right? So a catalyst doesn't actually react. It's not a product or a reactant. Okay? And notice how the delta H stays the same. That energy doesn't change whether it happens faster or slower. It doesn't change. All right.
Does anything change in an exothermic or an endothermic?
No, everything's identical. It's just an endothermic. Yes, sir?
What do you label the forward and reverse reactions?
This is your activation energy of the forward.
Right.
from here to here, and then this is the activation energy of the reverse. Yeah. All right, let's go to the worksheet now. Actually, you know what I want you to do? I want you to get with a neighbor, so pair up or someone behind you, and compare your answers to the homework. I'll give you a couple minutes, and then we'll go over it. Ah, you found them.
Yeah.
Where were they?
In with rocks and minerals. Does that make sense?
In with the rocks and
To me.
minerals.
Where do you want me to put this stuff? I don't want to put it in your way.
Right over there is good.
Alright.
Yeah.
Yeah, I mean, there's some that are kind of. I took some out already, so.
Okay.
A lot of it was like duds in there, but.
All right. Yeah. Well, I'll intro today a little bit.
Yeah, yeah. I don't know what I'm gonna do.
Well, I gotta go through my folders.
Yeah, I
and
might.
finish up scale solar systems.
Like if she stops in, I'm gonna go right into it. But otherwise, I'll try to do a little intro and then kind of hold it.
Okay.
Yeah.
That sounds good. Yeah. Why don't you at least start working on it right now? How are we doing? Are we explaining to each other? Is that how doing this? All right. Make sure you put that. Or can you see it, right?
Oh, I didn't do.
Please.
No, we're supposed to do the one structure. I don't think I got this one.
Yeah, this bottom one here is tricky. This bottom one's tricky. Okay, so don't worry about that right now. Okay, let's. I just wanted to kind of give you a little time to compare. Sometimes that helps some of you. I know in period 8, the joke is that Catherine Ray is a better teacher than me because she always explains to Destiny. If Destiny doesn't understand me, Catherine says, no, this is how it works. And so Destiny thinks Catherine should teach. So anyway, sometimes it helps talking to each other. Let's go over this side. This side first, okay? So I'm going to use this behind me. I don't know why I'm in front. I'm going to use the seesaw to help explain this. And then I got a demo that's going to help you understand even more because there's colors. Everyone likes colors. Here we go. So let's look at number 2. If we add H2, so let's look at this here. Let's say this is our N2 plus H2. This is our NH3, right? So we have N2, H2, NH3. So we're just going to imagine that's the seesaw here, the balance beam. So if I add more product or add more hydrogen, right? So let me take these off actually. Okay. So if I add no, I can't do it that way. Let's do it this way. Let's do it this way. So now let's start out. We'll start out balanced. We're balanced. But now we're going to add H2. We're going to add H2. So this side is too heavy. Which way does it shift? Raise your hands to go back to being balanced. That's right. To the right or towards the products. Right. So we could say towards the products, to the right, favors products, whatever. Okay? Good. Yes?
That's weird because like when I think of like shifting, I think of like it going.
Right, and yesterday I was talking to Brad about this, and he was a little confused because students think of it as this is the shift, right? So now it's like all going this way. So the way I want you to think of it is the stress happens. Something happens to the reaction. It's not balanced anymore. So what does it do now to shift back to being balanced? That's how I want you to think of it. So now this has happened. Now how does it shift? Well, yeah, one of these is going to have to shift over here to get it to go back to being balanced. So when we say shift, that's the shift. Yep, that's the shift. So it has a change, and then it shifts after that change. So now we shift to the right. Now, this is important what I just did. If I shift some of this weight to the product side, what did I just do? Raise your hands. What did I just do to the concentration of the N2? What did I just do to the concentration? If I took some from here and put it over here. Zach. I decreased it, right? I took some away, and I had to add it over here. So the next box, N2, decrease. Concentration decreases. But, Luke, what happens to the NH3? If I'm taking some from here and adding it over here, what happens? It increases. So the NH3 increases. So whichever direction you shift towards, the concentration goes up. Whatever side you shift away from, that concentration will decrease. Okay? So I'll do this again. Yeah, I'll do this again with the example with you. Then I'm going to go through the rest kind of out loud to pick up the pace a little bit so we can get through some stuff. So here we go. Number 3. This time I'm adding NH3. So here's some NH3, right? We'll put it here. Put it there. That's not the shift. So now, which way does it shift, Caitlin? To go back to being balanced or at equilibrium.
To the left.
Right, shifts to the left. So for adding NH3, we should have shift to the left, right? So, correct? Shift to the left. That means we're going this way. So I have to take some of this and shift it over here. Except I'm not going to put it down. The weights, it doesn't always work perfect. So we're going to imagine I put this on, okay? It's just I don't have small enough weights to balance it out. So we took some and we shifted it. So now we shifted this way. So if I took some from here, what happens to this concentration? It will decrease, actually. If you add more, it'll eventually decrease, which is weird. You didn't have to answer that for 3. They had a line through it. But what happens to the N2 and H2? Increase, right, Abby? You can see, right? What's going on here? So if we take some from here, shift it to the reactant side, it's going to increase these. Hopefully that's making some sense to you. All right, let's do the rest out loud. Number 4, can anyone do all those? Go ahead, Justin.
If you remove H2, the
N2.
equilibrium N2.
Yep.
The equilibrium shifts left.
Left, yep.
And the H2 increases.
H2 increases.
And the NH3 decreases.
NH3 decreases. Good. What about 5, Sydney? Well, we can maybe do this one again. If I take some of this off, so I remove H2, which way does it have to shift now? Well, what? Let me rephrase it. Am I going to shift some of this to this side, or am I going to shift some of this to this side? Which way is going to help it go back to being balanced? Right. So which way is that shifting? From your perspective. Left. Right. So we are correct. Keep doing that. We're shifting to the left. Right. That's my habit. Right. So we take this and we shift it over here. Now it's back to balance. So when I take away some H2, I'm taking some off of this side. It's going to be like this. So we have to shift some here to go back to being balanced. Okay. So we're shifting to the left in number 5. And if we're shifting to the left, what happens to the concentration of N2? It goes up. What happens to the concentration of NH3? If we're shifting it over here, this side will decrease in concentration because I'm removing some of it and shifting it to this side. So for 5, it should be left, increase, decrease. And then number 6, we're going to remove some of the NH3, so I'll take this off. Now we're like this. Which way do we shift to go back to being balanced? To the right. We have to shift to the right. Now we're being balanced, right? So if I take some of this here and put it here, again, the weights don't work too well, but if I shift and put it here, it'll be back to being balanced. So I shifted this way. So for 6, we're shifting right. N2 and H2, this side, they're both going to decrease in concentration because I have to take some and put it over here. Okay? Questions on that?
It's hard to do with not looking at that, just looking at
Yeah,
thing.
I agree. And that's why we do this in class and we get used to it and then hopefully we get better and we don't need it, or you can visualize it, or you can draw it, or you can use your pen or whatever, okay, or your hand. Flip it. Let's just go over the top one because the bottom one I totally forgot. It's called a common ion effect. We won't get to that till probably Monday. Forget that bottom one. So I apologize. Let's do the top one. Here we go. I'm going to kind of zip through this to pick up the pace. Number 2, add I2. We're shifting right. H2 decreases. HI increases. Number 3, we're going to shift to the left. H2 increases. I2 increases. 4, we're shifting left. I2 increase. HI decrease. Number 5, we're going to be shifting left. H2 increase. HI decrease. Number 6, we're going to be shifting right. H2 decrease. I2 decrease. And if you were making some mistakes, that's okay. We got plenty of more practice coming up. Alright, so hopefully the answers made some sense. Any burning questions there on that side? Anything you really want me to go over before we move on?
Can you do HI?
Which one? 3?
6.
Number 6. Okay, so let's say here's our H2 plus I2, and here's our HI. So if we remove some of this, okay, so we take away the product. So now we're like this. We have to shift to the right. Does that make sense?
Yeah.
And if we're shifting right, whatever we're going towards, we make more of that, and then we're using up all of this to make that. Good question. Any other questions? Again, K, that K letter there, that's called an equilibrium constant, AP Chem. Some of you want to take that in a couple years. There's a huge unit on that, but not in Regents. So it's confusing. We're not going to get into that yet.
I'm confused with looking at the board or whatever.
Yep.
So if you start out, are they all like equal?
Yeah, when you start, when it starts, it's like that.
So
Yeah.
when you're reading this, it's like all this.
When you're reading, 1, 2, 3, 4, 5, 6, you're starting balanced. And then it says, okay, you're balanced. Let's add H2. Let's add HI. Let's remove I. So then it's going to screw up the balance. So you're starting balanced every time. And then when you add something or remove it, you're tipping it. You're tipping that seesaw.
Are we ever going to do ones where it's
No, it always starts balanced. Always starts balanced. Good question. Okay, take out your notes, please. I'm going to replay the second half of that video from yesterday because it's talking about pressure. While it's doing that, I'll kind of get the demo set up, and then I'll show you that demo too, which kind of helps. It's another example. It's a chemical reaction of this equilibrium stuff. So lights, please. Blinds, please. Did you win? Good. All right, here we go. All right, so still not ready to jump yet, Luke.
I'll get it.
No, that's right. I don't need to be jostling my shoulder around. Started some new PT stuff yesterday. Hurting. All right, here we go. Changes in pressure. So we did concentration for homework. We concentrated on that. Okay. So now we're going to do some pressure today, and if time, we'll start the temperature too, because those are the three, right? Concentration changes the equilibrium, pressure, and temperature. So just pay attention. You don't necessarily have to write anything down. Just make sure you're paying attention, because I'm going to start talking about this afterwards with some examples after the demo.
The stress to a system at equilibrium is only applicable to gaseous systems. For this stress, we will examine another hypothetical reaction at equilibrium, where reactant A reacts with 2 moles of reactant B to form product C and product D. An increase in pressure means that there is a decrease in volume, so there is less space. Equilibrium will shift to the side of the reaction with fewer moles. In our example, an increase in pressure will cause equilibrium to shift to the right, since there are fewer moles. 2 moles compared to 3 moles on the left. A decrease in pressure means that there is an increase in volume, so there is more space. Equilibrium shifts to the side with more moles. So in our example, equilibrium shifts to the left.
This is confusing. So I often tell kids, I don't like telling them this, but I often say try and memorize that if you increase pressure, it shifts to the low number of moles. If you decrease pressure, it shifts to the higher number of moles. Now, the reason it does that, so stay with me, try and clear your mind of anything else you're thinking of, try and listen carefully. The reason it does this is when you expand a system at equilibrium, let me back up. Before you expand or compress, before pressure changes, there's a certain amount of space between those particles, and they want that space. So if you cause it to expand, it doesn't want to be that far apart. It wants to be closer together. So if you force it to be further apart by sucking out the air, by releasing pressure, the particles are too far. Well, how can they get closer together? Well, if they all shift where it's more crowded, this side, there's more moles, so it's more crowded, they'll be closer together again. So when you decrease pressure, they shift towards the higher number of moles, so that spacing is the same again. And then the opposite's true. If they have a certain space and you squeeze them together, they don't want to be squeezed together. They want to be back to that certain space. So what they do is they shift where there's more space, to the side with less particles, less moles. So instead of being cramped, they can go back to that original spacing. So hopefully what I just said made a little sense, because that's the only way to explain it and the only way to really grasp it without just memorizing. So the video is good because it has these little animations. I'm going to stop it because she's basically done there. Let's see if we can do some practice problems and see if you can get the hang of it. All right? So blinds, please, lights. I'll show you the demo and then we'll get to some practice problems. All right. So let me show you a chemical equilibrium. This is called an indicator. Bromthymol blue. Bromthymol blue. In here is an acid. When I put this indicator in the acid, what color does it turn? Yellow. Everybody see that? Very obvious, it's yellow, right? Okay. Watch what happens when I put some base in there. A little bit more. I'm breaking a very important rule right now. Safety class, right. I always remember my teachers in high school and college would never do anything safe. They're like, you have to do it. Ah, but it doesn't matter for me. Oh, not enough. What can you see happening? Yeah, it's getting what? Purple, blue, right? Okay, so now it's all blue. Now watch what happens. Watch what happens. I'm going to put more acid back in. Take a few squirts here. You don't want it to be yellow? I want it to be yellow. But you know what's going to happen. That's good. So if I keep adding the acid, someday, maybe by the end of the period, it'll go back to being yellow. And guess what happens? Guess what happens if I add more base? Go back to the blue or the purple. I could do this all day. I just want to sit here and not do anything else today. I could play with this. It can go blue, yellow, blue, yellow. That's a great example. You may not fully comprehend it, obviously. We haven't learned acids and bases. But that's a great example of equilibrium. Here's what happens. You have your acid and your base in equilibrium. You don't have to write this. Just watch. Your acid and your base are in equilibrium. Well, if that indicator plays a role, this side's yellow, this side's blue. It's very hard. I tried doing it before school. I couldn't get it to work. Certain acids and bases don't work very well. It's good to show you that I can shift it, right? I can shift it. But what do you think it looks like if it's right in the middle and it's nice and balanced? This is more like an art type thing with colors.
Greenish.
Greenish, right. But let's think about it. When I added the acid, okay, when I added the acid, what happened? It shifted, right? Equilibrium shifted. If I added the base, what happens? Equilibrium shifted, right? And the colors I used the acid base and the indicator to get the color to show you. Here I can show you shifting weights and it can go back and forth, but the colors, that's a good chemical one. All right, there's not too many good demos for that. But anyways, I wanted to show you that so that you could literally see me increasing concentrations and see what happens. All right, let's do an example of pressure now. Now, yesterday, what's the reaction we had? N2 plus H2 yields NH3. Is that the one we used? Okay. Let's use a different one here. Let's go with N2 gas plus O2 gas in equilibrium with N2O4. And what are we going to need here? We're going to need two of those, right? Is that balanced? Yes. Okay. Alright, so here's your equilibrium system. Here's your reaction at equilibrium. Here's the question. See if the video and what we've been saying makes sense. So, if, write this down, the pressure on this reaction is increased, in what direction will the equilibrium shift? And then, next question. I want you to write your answers down. I'm going to come around and check it. In what direction will the equilibrium shift? So that's the first question. Second question, how does this affect? So this is more like 1A and B, I guess. So based on your answer to number 1, how does this affect the N2 concentration? Those brackets, should have explained this on the homework, those brackets stand for concentration. So when you see a bracket around something, it literally means concentration. So if I wrote N2 concentration, the word concentration, that's the same thing as N2 in brackets. Okay? So we didn't write a law, we didn't write a definition. I showed you the video, explained it a little bit. So let's see if you can do this. If the pressure on this reaction, and if not, we'll go over it. If the pressure is increased, in what direction will the equilibrium shift? And then how does that affect N2 concentration? So I want to see you are fast. Maybe we can help some people out here. So what did the video say, Abby? About if we increase pressure, which side does it shift towards? The higher number of moles or the lower number of moles? Do you remember what the video said? Say it again? Lower number of moles, good. So if the pressure is increased, this will shift towards the lower number of moles. The lower number of moles. Now, which side is that? Who haven't I talked to a lot? Althea. Which side has less moles, the reactant or products? Right, good job. We have 3 moles over here, and we have 1 mole over here, right? Right, 3 moles and 1 mole. So, based on what Abby said, Sydney, which way does it shift? To the right. Very good. It favors product formation. It shifts to the right. It shifts to the right. How does this affect the N2 concentration? Let me back up. Let me explain why. Why does it shift to the right? Again, the best way I can show you, the particles are this far apart. If we squeeze them together by increasing pressure, they get closer. They don't want to be closer, so what they do is they all say, let's go over here. There's more space. They all go over here so they can spread back out because there's less particles on this side, right? So the concentration, I shouldn't use that word. The spacing of the particles can be bigger because there's more space, less particles. That's why they shift to the right. Okay, so now, back to this. Now this works. Now we can use this. That first question, you can't use this. So now, if we're shifting, I can take all these weights and put them over here. We're shifting this way, okay? I don't want to because it's balanced and that's not exactly what's happening, but let's visualize it. If we take some of the reactants and make products, so we're going this way, what happens to the amount of N2? It decreases. Good job. N2 decreases because we're shifting away. We have to use the reactants to make the products. So when you use up your reactants, which part? Number 1 or number 2 or both? Number 2. So if we are, so this right now is here, okay? What we're doing, actually forget that. That might be confusing, so let's not go down that path. So right now it's balanced, but when you put pressure on it, it gets all screwed up. So what happens is this happens? All of these, whatever's on your reactant side, start coming together to shift and create N2O4. So if I'm making more of this by shifting this way, I'm making it out of these two.
Because there's 3 moles of that one outside of these two.
Right, so we're shifting this way. And you know, sometimes I think of Legos as well. If these are like your individual pieces, you're going to put them together to make the bigger structure. If you keep making more of the big structure, you're not going to have any individual pieces left. So this is going to get used up, and that's going to get greater. Does that make some sense a little bit? Okay? Okay, good. Another question. We'll use the same reaction. Same reaction. Okay, so we'll do one more practice problem, then we'll write the law, the concept there. Okay, so next question here. If the pressure is decreased, if the pressure on this reaction is decreased, if the pressure on this reaction is decreased, how is the O2 gas concentration affected? So I'm kind of putting 2 questions in one here. The first thing you have to do is figure out which way it shifts, and then you have to think about how does that affect the O2. Again, some of you, I think sometimes don't like to write questions down because you're getting lazy about it. Make sure you write the question down, otherwise the answer makes no sense. So this time we're decreasing the pressure. Okay, we're going to steal that little phrase from that Miss McGovern reminded me of this year. Think, pair, share. Pair up. Talk to each other. And then I'm going to call in a group to explain to the class. You 3 work together. Actually, no, you 2. And then you 2. You 2. You 2. You 2. I'm with Althea. Althea gets me. She has the best partner. Okay, what do you think? That's okay, go ahead. So, we're going this way. Okay, good. So then how does that affect? Okay, so, yeah, when the pressure is decreased, you are correct, it's going this way. So that's the only thing that happens. Once you figure out the shift, that's the only thing that happens.
I get the shift part after this.
You're lucky, I won't call on our group. Who's it going to be? What's up, John? How are you doing? Getting some gum, alright. Need some gum. Justin, Destiny. Desiree, sorry. Sorry, I knew that was not going to be good. Sorry. What do you guys think? It shifts to the left. Tell us why. Good. It goes to the higher number of moles, so it shifts to the left. Good job. And if we're shifting this way, what'd you say? What happens to the concentration? It increases. So O2 increases in concentration. So again, good job. If you take some of your product, shift it to the reactant, you're going to be making more of the reactants and using up your products. So what I want to do is write the law, the rule real quick. But in case I get cut off, your homework tomorrow, due tomorrow, same worksheet. So take this out and make sure you know which ones to do. You're going to be doing number 9 and 10 on this side. 9 and 10 on the side with one chart. Okay, again, we didn't get the temperature, but that's okay. 9 and 10 on this side, and then flip it on this side with the two charts. You're going to be doing 9 and 10 on the top chart and 7 and 8 on the bottom chart. Okay? Yes, sir.
Top one, there's 2 moles on each side. So
Shh, John Todd, you're ruining all my fun.
But you didn't-
I know. I wanted you to try it on your own. He already ruined it. If there's 2 moles on both sides, what do you think happens? Nothing happens. Right, it doesn't shift. Good job, John Todd. All right. So let's try and squeeze in the law really quick, but I'm going to run out of time. So you can pack it up, but don't get up, don't move, listen to what I'm saying. So tomorrow we'll go over the pressure, those pressure problems. Then we're going to learn about temperature. But first, what do we have as soon as you get in here tomorrow? Quiz on potential energy diagram. I am after school, all right? But then tomorrow, again, after that quiz, we'll learn about how the temperature affects equilibrium. All right? Any other questions for me? Last minute questions? You can just wait. There's like 30 seconds-ish left, all right? So, what can I... Oh, catalyst. True or false? Catalyst changes the reverse activation energy.
Yeah, it does.
Yeah, it does. It lowers the bump, right? True or false? Catalyst changes the delta H.
False.
False. Good. The amount of heat stays the same. True or false? A catalyst will change equilibrium. What does a catalyst do? Speeds it up. So this whole balance thing just happens faster. It doesn't actually change it. So we'll talk about catalysts tomorrow as well, too. All right, we're pretty much good to go. Oh, what else is due tomorrow? Journal, review book 4. Review book 4. Okay, don't forget. Have a wonderful day.
Oh yeah?
I saw a Mustang yesterday around here that was literally deep
Thank you.
All-star lesson. Awesome.
Thank you.
I wish I had you for my chemistry teacher. I probably would have done much better.